Good morning. This is Module 3, the first lecture, Part 1. There we go. Okay, you should have, for the 15th time, you should have 2 pages of notes, front and back and up front. So a total of 3. You should have 2 periodic tables and 1 test, all right? And so quick in terms of the test, just to go over it. And that goes for you guys zooming too. You should have those pages. I emailed them to you in PDF form. And if you don't have 2 pages of notes, 1 test and 2 periodic tables, holler at me and I'll send them again. So the test, pretty straightforward. Again, I mentioned to you we were doing no calorimetry, so the hardest part of the module we've just opted out of, the purpose of which I see no purpose in the calorimetry. So, but the stuff that we did look at, you'll need to know, and in terms of some of those calculations that we did, and just in terms of what was in your notes. That's pretty much what we do for the test. I don't bring surprises to you. I test you over the stuff that we go over. I test you over the topics in the notes. That doesn't necessarily include all of the calculations. It will include the formulas and our discussions of them, but that's what your homework's for, in terms of practicing the problems so that you can do them when it's time to get examined over them. So, and you can use your notes and your homework to refresh you in terms of how to do that stuff. So again, the purpose is the learning, it's not the memorizing, all right? Is there questions about Module 2? Anything that we did that you want to go over again? All right, well, good. So here we go into Module 2. If you would, turn to page 69 in your textbook. This is a fun module. I think so. You know, some of them are, that's not a hand back there, is it? All right. Some of them just interest me more than others. Again, the ones that are heavy in the math, that's just not as exciting to me. But interesting nonetheless, but it's just not as exciting. But this is a discussion of atoms and molecules, so we're finally getting to the crux of chemistry, and so that's what we're going to do. We're going to jump right into that. And just as a reminder too, so you know what I told you as we began the course, you had to do quite a bit of writing in the first module as I read off definitions and these sorts of things from your textbook. The purpose of which was to familiarize you with the textbook, to give you a sense of how it's written, to get you into the textbook. And I want you to continue to emphasize that, to read it. You know, some of it's dry, but this guy is pretty good. And this edition, why do I use an older edition chemistry book? Well, number one, the information is the same as any newer version. And number 2, it's just so very well done. The guy is interesting, he's funny. So I highly recommend you read through the textbook as you go through this stuff too. So here we go. Let's talk about the continuous theory of matter. You know, human beings have been thinking about the way that stuff is made, how it's made up, for as long as human beings have been here. And an idea surfaced by Greek philosophers. It's basically described the continuous theory of matter, and that idea was that substances, and I'm reading from your notes, substances are composed of long, unbroken blobs of matter, all right? That it's what exists, in spite of the fact that it can come apart, all right, still is basically the same thing that has just come apart, all right? So sand on the sand on the seashore versus the tree in the forest. It's all the same stuff in terms of the unbroken broken blobs of matter. They're all sort of the same thing ultimately. So that was one idea. And then another idea came along, and that's pretty much, again, these are great big concepts, not in the sense of their weightiness, but just, a large summary. The discontinuous theory of matter says that it's the idea that substances are composed not of one long, unbroken blob of matter, but of tiny individual particles. And of course, you understand where we're going and why that is true, in the sense that what you've learned thus far in your life, you know that to be the case, that in fact what exists is made up of very small things that come together for a certain period of time, but then can disassociate and then come together in other forms. And so related to that, if you turn over to page 70, is something else. And this is one thing that you're going to have to write. There's, I think, 3 or 4 in terms of this module. So there's not a lot of stuff to write in your terms, but this is one of them. And I wanted you to write it because, well, just because. It is the law of mass conservation. And this is the definition of the law of mass conservation. And there it is on page 70. Mass cannot be created or destroyed. It can only change form. Mass cannot be created or destroyed. It can only change form. Sounds a little familiar, doesn't it, in terms of something that we've talked about not too long ago? As a matter of fact, from Module 2 on page 40, the first law of thermodynamics says this: energy cannot be created or destroyed. It can only change form. So, isn't that interesting in terms of our reality? Not only energy, but the stuff of life, the matter of life, cannot be created or destroyed. Well, it can be created. God did that. And interesting discussions about origins. As a matter of fact, most honest agnostic or atheistic type folks have to admit that they have no answer for the existence of stuff, matter at all. They have no answer for it because they recognize that something has to have the power to not change. It's in philosophy, it's called the power of being. Something has to exist in and of itself without ever changing to be able to create something that, as we know, all matter does change. It changes forms all the time. Something has to exist to have brought what exists into existence. And secular science has no answer for that. And they'll skate around it. They'll, speak in just pejoratives, but they have no answer for it. And of course, we understand there is an answer. There is a God who does have the power of being, who stands outside of his creation and created it. And so he did in fact create the matter that exists, but no one else can, and no one can destroy it. As a matter of fact, it simply changes form. When we discussed the types of energy in the last module, we talked about potential energy and kinetic energy, and we used the classic example of burning a log. And so what you might be inclined to think is that as you burn a log, as it undergoes combustion, a combustion reaction, which we will study in a few modules, that matter is being destroyed. We're burning it up. And as it turns out, that's not the case. What's simply happening is the matter is changing form. It's turning into gases. water vapor, and that dreaded, terrible poison, carbon dioxide. But carbon dioxide, and then ash, which is carbon and calcitrate and phosphate, and a variety of things can make up ash. But in any respect, the matter has not been destroyed, it's simply changed forms. And so that is the law of mass conservation. The mass of a substance equals the mass of its essential elements, of its basic elements. So if it's got two different elements, like I've written for you on your notes, element A and element B, then you add the mass of both of those elements, and you've got the mass of that substance. Yes, sir?
If you had three different things, you would have mass of element A, mass of element B, and then mass of element C.
You still got it. Add those three things together, and you've got the mass of a substance. As a matter of fact, let's, in terms of identifying that, turn over to the next page. Look at example 3.1 on page 73. So it says, a chemist noticed that when given enough energy, a certain white powder changes into two different substances, tin and oxygen. And the chemist watches 151 grams of that powder undergo this change. The chemist easily collects the tin that was formed out of that compound white powder and measures its mass to be 119 grams. Unfortunately, the chemist couldn't collect the oxygen that was formed. It went into the atmosphere for you to breathe and could not determine its mass. Use the law of mass conservation to help the chemist determine how much oxygen was made. So, in terms of the answer to that problem, it is a simple addition and subtraction problem, setting it up such that you solve for what you're being asked for. So you're given the total, 151 grams. You're given one of the ingredients, 119 grams. So you know in order to solve for the other ingredient, you got to subtract the one ingredient from the total. And that's what they do here in the example. And they walk you through it. One more thing, I don't think I mentioned this last time in the last module. These examples are really helpful because they take you through them, and the on your own questions aren't too bad either. They give you the answers as well. But the example questions take you through step by step. So if you're struggling with any of this stuff and you don't want to call or email, look at these examples. They'll walk you through some of these equations that we're asking you to do. And again, I almost think this doesn't even qualify as an equation because it's just addition and subtraction. Yes, sir?
What are the significant figure rules for adding and subtracting?
I'm sorry, one more time.
What are the significant figure rules for adding and subtracting? Yeah,
we avoided significant figures.
Okay.
We did. We are uninterested in them in terms of this course. That was module 1, I think, wasn't it? Yeah. So I just, like I say, there's certain aspects of the thing, of what he does that in terms of what we're doing, I see no need. But thank you for the question. Good question. Good question. All right, let me stop there. So is there questions about this stuff in terms of what we've discussed so far? Simple concepts, profound concepts for millennia. So we happen to live in a time when these are simple concepts, but for many, many years people had no clue about this reality. But the continuous theory of matter and how that works in terms of the law of mass conservation. So again, stuff changes form, but it never ever goes away. All right, questions about that? Good, good. All right, let's keep going. Decomposition. On page 74, if you would. So we will look at decomposition reactions. Chemical equations and reactions are coming. And I actually like that stuff. It does involve some math, but it's kind of interesting stuff in terms of following the bouncing ball, in terms of how much stuff is used and how much is produced. But we're not there yet. So, but decomposition is a form of the chemical reaction that you will be asked to understand in this course. And it simply means the process by which a substance is broken down into its constituent elements. And that's the way we're going to define it for this module. We'll find that decomposition reactions also break down not only into elements but into compounds. All right, that's a couple of or a number of elements. But that's decomposition. So, but I just used a word that we haven't defined yet, and that is the elements. So, any Toby Mac fans here? So, great album, as a matter of fact. The Elements. So, he was here in concert last year, or a year and a half ago. So, if you ever have a chance, see Toby Mac in concert. That's a concert to have. So, anyway, no extra charge for that. But, so, an element is any substance that can't be decomposed into less massive substances. So we will find out that you can sort of break down an element a little bit. You can change it. We will discuss that in the modules to come. I don't want to go any further to confuse you. But for now, it's any substance that cannot be decomposed into less massive substances. All right? Elements. That's what they are. All right, now we're getting into some meat right here. So on the bottom of page 74, you have the bolded statement, periodic table of elements, and I've actually asked you to write this down. So let's define the periodic table of elements as a compilation of important information concerning each element. You could say known to man, but each element is fine. So a compilation of important information concerning each element. Just write that down. So there on page 75 is a very pretty periodic table of elements. If you go to the very front page of your textbook, well, not even front page, the opening, whatever that's called, inside the hard cover, all right? Why, there's the same one, all right? So there is the periodic table of elements. I have handed you two. One is a photocopy of the one in your textbook, all right? You all have it anyway. But sometimes it's easier to have it clipped in your notes to refer to as we go through this stuff. And a second is to help people like me who don't remember well what the symbols are for the elements. Well, looky there. They're written right there for you on this second periodic table. So if you ever wonder what some of those things are, what's B? I don't know what that is. Wait a minute, it's boron. All right, so there it is for you. And this periodic table offers a little extra information, some of which we'll mention as we go through. Not really more than this one, in the sense that everything that we're going to need to know in this course is listed on that particular copy of the periodic table. It does not contain as many elements, as you will immediately notice, as this later version. Let's see. Yeah, they've got up to 118 on this later version, and there could very well be more. I photocopied this one a couple of, probably 4 or 5 years ago now. So all they're doing is creating these things in the lab in terms of adding protons and electrons to create new elements. So these are not naturally found elements. So again, interesting if you're going to pursue a career or a degree in chemistry, but not for our case. So you have your copy of the periodic table. It contains lots and lots of information, some of which we're going to introduce in this module, and more of which we will introduce as we go on. So have all of you been introduced to the periodic table before? Have you seen this before? So some of you are nodding heads. Yeah, good. So you've had an intro to it. So this will be helpful in the sense of reminding you. So I've got some information. This is out of the text. Again, 92 elements. Numbers 1 through 92 appear naturally in creation. Anything over 92, again, in terms of this particular, oh, wait a minute, it goes up to 112. What am I saying? So this particular one goes up to 112. The other one goes up to, what did I say, 119? 118. Anything over 92 is man-made, artificially manufactured. The element abbreviation, which appears on the periodic table, is usually either the first or first two letters of the element's English or Latin name. All right? So that makes sense for a whole slew of these. Back to the cheat sheet, to the cheat page, all right? Look at the names on this thing. So you start at the top, there's H for hydrogen. Ha! Got that. That's easy enough. Number 2, on the right upper corner there of your periodic table. HE for help with this course. No, that's for helium. All right, so again, that makes sense. Li, number 3, back to the left of your page, the first column. Lithium makes sense. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, Ne for neon. So all that makes sense in terms of the English. But then we come to look at the first column, column 1, row 3. There is Na. And you say to yourself, what the heck is Na? And it's sodium? How can that be? Well, again, we just had it explained. It's either the first two letters from the English or the Latin. So that's what's happened there. And so in terms of understanding those things, that's simply what you have to remember. And by virtue of what you do in the course, by virtue of working with the, well, in this case, in this module with the periodic table, modules to come, working with the chemical equations, you will become familiar with a lot of these elements. You just will. You'll recognize them for what they are without staring at this thing and having to memorize it, okay? Let's go down the rest of the description and then I'll stop and see if you have any questions. So notice, back to, and it's on your cheat sheet periodic table, but it's especially prominent here on your textbook one. Notice the heavy stair-step line beginning at boron, that's number 5 in column 3A, and moving diagonally down the table to astatine, AT, there at the bottom. All right, you're taking steps all the way down. All right, you're going to the basement of the periodic table. Well, that's because you're separating the elements into two very important classes of elements. Metals, all right, which is to the left of the stair step, of the heavy stair step. The exception, of course, to that is at the very top, column 1A, and you notice it's the same color as those that are on the right side of the stair step. So there's your exception. You'll also notice the yellow in the middle, and we'll briefly talk about that, but the course does not go into those elements a lot, all right? And any introductory chemistry course does not deal with the with columns 3B through well, really the 8 columns there in terms of the yellow. We'll introduce them in just a second. But the bottom line to it is the metals are to the left with the exception of hydrogen, and the non-metals are to the right. And so if you sort of think about it for a little bit, number 30 is zinc, so you immediately sort of think of that as a metal, right? Aluminum, number 13. So yeah, you pull out your roll of aluminum foil and you immediately recognize that as a metal. Magnesium. So you think about some of those things and they sort of come to mind as being metals. And then to the right, the non-metals, you think about those. Oxygen, not very metallic there, right? Fluorine, neon, helium, hydrogen. Again, you can't really conceive of those as being metals, right? You just can't. So those distinctions are important. It is, if you haven't heard it before, you just did, and if it seems difficult, it shouldn't, and it won't be, because you're going to work with them quite a bit. So here's some basic attributes of metals and nonmetals. Metals are malleable. Again, I mentioned aluminum foil. Think of how you can bend that stuff around and make all kinds of stuff, you know. They can be bent in shape. They have luster. They're shiny. So what's fun about aluminum foil is it's got two versions, right? It's got a shiny side and a not so shiny side. And it can conduct electricity. So, you know, electrical wires are not made of solidified oxygen, all right? They're made of metals. They conduct electricity. Nonmetals are typically brittle. They break when you bend them, all right? They lack luster, all right? They're kind of dull. And then nonmetals also do not conduct electricity. Now there's very interesting exceptions to a lot of these rules that we're gonna discuss as we go through chemistry. Have I given you my spiel about that yet? I don't know if I have, but so we're gonna find that, as in life, in chemistry, a lot of these rules or a lot of these laws, a lot of these facts, there's exceptions. And it just makes the course either, well, you can approach it one of two ways. You can approach it as maybe you can tell the way I approached it, and that was you can either pull your hair out or you can just say, well, that's interesting. Isn't that kind of cool that this can be so and not so at the same time and yet not be contradictory? So I don't recommend the pulling the hair out routine, so don't do that thing. But you can approach it one way or the other, but that's just the facts in terms of the study of chemistry. We're going to find some things to be true in certain circumstances with certain things, and then in other instances to not necessarily be the case. All right? So let me stop there for a second, see if you've got any questions, anything at all about that stuff. Anything at all? Let's keep moving then. Let's define the metalloids. All right, these are metals. These are elements that have some metal properties and some non-metal properties. Would you write those down? Write that down for me. So that's one of the exceptions that I was just describing for you. They have some properties that are metallic and some non-metallic properties. That's a metalloid. Yes, ma'am.
I have a question.
Yes.
So you said non-metal things can't conduct energy.
Can't conduct electricity.
Yeah, cannot conduct electricity if they're non-metal. How does water conduct electricity?
What was that? One more time.
How does water conduct electricity?
Water conduct electricity.
Yeah.
Can you wait for just a little bit of time with regards to that? We've got a whole spiel about that. Because water is composed of what? It's two nonmetals, oxygen and hydrogen, right? And yet, are you going to get in a small tub of water and allow somebody to throw a plugged-in, turned-on hairdryer into that water? No, you're not. And yet, the rule says that water cannot conduct electricity based on the fact that both of those are nonmetals. Well, there's some interesting chemistry involved with that type of water, which we will discuss in, well, not too long. So could you mind waiting? Yeah, all right, but excellent question, and thank you. Thank you, yeah. Water is another one of these exceptions to things, not necessarily in this instance, but it's just a fabulous compound, and we will look at water. In fact, life as we know it could not exist unless water has the unique qualities that it has. All right, we'll discuss that as we get there. It's another evidence of the fact of God's creation, of God's hand on this thing. You and I would not be here if water did not have the capabilities that it has. So I'll just stop there. Maybe that will entice you to what do you say? Sometime in the future. All right, so we just defined a metalloid, a compound. Here's the definition for that. A substance that can be decomposed into elements by chemical means. Oh, would you turn over to page 79? There's the definition of compound on page 78. And so we've got the definition of compound, and then we're going to discuss that in a little more detail. And now we're running out of time. Let's see, how are we doing here? We're not doing too bad. We've still got 2 pages of notes to go, but actually the second page is going to fly, and the third page is Naaman, so we're actually okay. So let's do another definition. The law of definite proportions. And that's, I gave it to you too. Used to have folks fill this stuff in, but like I said, I decided I didn't want the course. I never liked any class that required me to either on a keyboard or with my hand and a pencil to be busier than what the professor was saying. I always like to listen to what they have to say as opposed to have to write fast. So the law of definite proportions says this: the proportion of elements in any compound is always the same. So in terms of that, the law of definite proportions, it is defined, and I the pictures tell 1,000 stories. I like the pictures. So in terms of making table salt, all right, table salt requires a certain amount of each compound in terms of the production of it. And so if you had 10 grams of sodium and you had 10 grams of chlorine and you did the chemical reaction to make salt, formation reaction, you would produce 16.5 grams of table salt of sodium chloride, but you'd have some leftover sodium. That's because in order to make sodium chloride, to make table salt, it requires a specific recipe, a specific chemical recipe, a specific amount of mass of matter for each one of those components in table salt. And so if you have 10 of each, you're not going to make 20 grams of table salt. You're going to make 16.5 grams and have some leftover sodium. But what if you had 6.5 grams? I'm at the bottom, pretty little picture in your textbook. If you had 6.5 grams of sodium and 10 grams of chlorine, and you did the formation reaction of those two, what's going to happen? You're going to produce 16.5 grams of salt with nothing left over. You had a perfect mix in the recipe, so to speak. And then the last depiction there on the next page in terms of the ratios of the recipe, all right? And we're near the end of the class, and I wanted to have you come up and show me your homework in terms of Module 2, if you've completed that. And I'll give you your test from Module 1. You have your test for Module 2. That's due next time. We'll continue in this stuff, and we'll look at the proportions in terms of the math of it. Again, all we're doing with this stuff is ratios. So we will introduce that the next time, or just remind you, really, it's not hard stuff. And we'll go from there. All right? Is there any questions about what we talked about thus far? All right.